Okay, apologies, I forgot to introduce myself when asked the question, but anyway, Fred's done it for me. So I'm Paul Nelson. I'm a soil scientist here at James Cook University. I'd like to thank Annette for a really great introduction. I learned a lot and it's very useful. And I'd like to echo Fred in thanking our sponsors, thanking all of you for coming, for participating. I'd like to thank Fred for keeping us on track, and especially thank Angela for all the huge amount of work she's done organising this. So thank you. Okay, so Binoy, Sarkar, Wolfram Buss and I were the organising committee, and we're very happy to see lots of submissions for this symposium, and we're delighted that you're all here now and that we've started. So this morning I'd like to give a bit of background on enhanced rock weathering, and I thought, as a matter of interest, who'd heard about enhanced rock weathering 1 year ago, more than 1 year ago? What about more than 5 years ago? That's 2021, if you can't do your maths. Okay, interesting, yeah, so it's a growing area of knowledge, and good to see you all here. So let's take a quick journey from the beginning of the Earth to here and now in Cairns. So soon after the birth of the Earth, about 4 billion years ago, there wasn't yet any life, and most of the carbon on Earth was in the form of carbon dioxide in the atmosphere. The atmosphere was about 80% carbon dioxide. Early in the Earth's history, the water cycle started, continents and oceans formed, and life evolved. And those processes led to weathering and photosynthesis, both of which took carbon dioxide out of the atmosphere to the current 0.04% we have. So I'm sure you all know about photosynthesis, so now we're going to dive more into the weathering side of things. So fast forwarding to the 20th century, that's when we discovered plate tectonics, which explained the cycles of uplift, mountain building, erosion, volcanism, and all those things that produced new rocks to be available for weathering at the surface of the Earth, where there's water and air and biological activity. And the mid-20th century was also when Harold Urey worked out this incredibly important link between the carbon cycle and weathering. So carbon dioxide dissolves to form carbonic acid, so that's aqueous dissolved carbon dioxide, and it reacts with the silicate rock. This is just a simple example of a silicate rock. It breaks down the silicate rock and you end up with bicarbonate and calcium, so dissolved ions, plus silicic acid or some other secondary mineral depending on the nature of that original rock you started with. So you can see here that for every, if you take 2 molecules out of the atmosphere, out of a gaseous form, and put it into solution. Now, that bicarbonate and calcium, or it could be another cation there, can combine together and precipitate out as limestone or calcium carbonate, and you get 1 molecule of CO2 produced. So enhanced rock weathering is all about this reaction, either going through to bicarbonate or going through to carbonate, and if you end up here, you've taken 2 molecules out. If you end up here, you've taken 1 because you've taken 2 but you've put 1 back. Okay, so in reality we're probably somewhere in between the 2 depending on how much bicarbonate and carbonate we get. So these reactions are the reason why most of the carbon on Earth now is in the form of limestone, by far and away most carbon is limestone, because this has been happening for billions of years. So now let's put people into the picture. So from about 300,000 years ago, we started populating the Earth, settling Australia about 60,000 years ago, and eventually settling in Northern Europe and Asia when the ice sheets retreated about 5,000 years ago. And we encountered landscapes of vastly different age. So from hundreds to thousands of millions of years in these red and purple colours, through to less than a few million years in the green and yellow colours. So then about 10,000 years ago, climate stabilised and agriculture, people started practicing agriculture almost simultaneously on every continent except Australia and Antarctica. And they started practicing agriculture from New Guinea through Asia, East Asia, South Asia, Middle East, Middle America, all at about the same time independently. And you can see that sort of corresponds with the younger geological materials, which is quite interesting. You know, you could think more fertile, etc. Here in far north Queensland, we're at this amazing boundary in human histories and decision making between the path to agriculture in New Guinea up here and no agriculture in Australia. So these people were talking to each other the whole time, we presume. They do now, and there was always a connection there. So the rest of the world was developing agriculture with all of its increasing reliance on external inputs like fertiliser and lime, and eventually fossil fuels, like just about everything else we do. I'm just trying to get my... And in Australia here, an increasing deviation from circularity of material and energy cycles. Well, in Australia, land management didn't involve those external inputs, but involved highly sophisticated relationships between people and land, including sustenance. Okay, that was the rocks. Now, what's more important is really for agriculture is the soils, because the soils tend to decline in fertility with age, with weathering. So if we look at this left-hand panel here, and we take this as the time when rocks are exposed at the Earth's surface, and I'm talking about alkaline silicate rocks because most of the focus of today is on that. There are other type of rocks, but we won't bother about them too much. So over time, the primary minerals in the rock disappear. They're dissolved by weathering, and you end up with some that don't weather very easily, like quartz, which just hang around for a long, long time. At the same time, pH declines, the soil pH declines. Cation exchange capacity tends to peak early when you have materials like allophane, smectites, which have very high negative charge. They form quite quickly, and you have a very high ability to hold cations like the essential nutrients like calcium, magnesium, potassium, and so on. So soils tend to be fertile when they're young. Over time, you tend to lose those minerals, and you end up with charged minerals like kaolinite, which have much less capacity to hold cations, and so the CEC tends to drop with time. The base saturation is the proportion of those cations that are calcium, magnesium, sodium, and potassium. So they're three essential plant nutrients. And that tends to be high initially because they're being released from the rock. So you get soils that have a high proportion of those important cations. With time, as the soils acidify, exchangeable acidity comes in, aluminium and hydrogen, which are toxic to plants. So the soils decline in their fertility as you lose that base saturation. During that time, you get the loss of primary minerals. You get an increase in variable charge materials, and they're materials which charge changes depending on the conditions, especially the pH. So organic matter and oxides are the main forms of variable charge materials, so they're important for fertility. Organic carbon tends to peak early because you've got those minerals that protect it, and fertile soils, so you've got high net primary production, so it tends to be highest early in these younger soils. And then as you lose those more protective minerals, it tends to decline, and you end up with a lower organic carbon. So over that sort of gradient in the US soil taxonomy scheme, the soils here are called ultisols and oxisols. You'll often hear that term. Now, Australia, a lot of our soils are sort of here. We're at this highly weathered end. Okay, some of our soils are not so weathered. In the rest of the world, you've got soil, like in the volcanic areas, you've got soils that look like this, that are very fertile, high CEC, high organic matter, etc. Most of our soils in Australia are down here. Now, if we add CO2 to the picture, the reaction I was talking about, the weathering reaction by carbonic acid or dissolved CO2, is very high initially, and it declines over time. And the highest natural rates that have been measured globally are around about 2.8 tonnes of carbon dioxide per hectare per year. That's been measured in a catchment that's fully basaltic material in Java, where the conditions are hot and wet, ideal for weathering, and that's the highest natural rate measured. Okay, so I want you to keep that in your mind, 2.8 tonnes of carbon dioxide per hectare per year. Which brings us to the 21st century, and we're talking about adding alkaline silicate rocks to reverse that process. And sorry, I'm just trying to. Here we go. Reverse that process to make the soils more fertile, rejuvenate them, and to take carbon dioxide out of the atmosphere. So Before I go on to that, I just want to go, let's stay in the 20th century for a moment, before the idea of enhanced rock weathering came up. So last century, we were already aware that adding crushed alkaline silicate rock improved the fertility of soils, okay? So we know that many soils are inherently highly weathered and poor. Agriculture tends to deplete soils, so we need to actively manage that fertility and replace nutrients and overcome the acidification. Now, we already knew last century that adding alkaline silicate rocks like basalt gives you a liming effect, so it counters acidification, can bring pH up. As the rock weathers, you get nutrients released like silicon, magnesium, calcium, iron, phosphorus and potassium, which are all essential nutrients. New clay minerals form, and so we know that clay minerals are critical for soil fertility, so you get new clay minerals that are forming. And the capacity of the soil to retain organic matter can also go up, basically due to these things up here. So they're all good things that we've known about, and Peter Van Straten in Guelph University wrote a book about it. And here in North Queensland, there was some really nice work done by Ross Coventry and JCU and Gavin Gilman in CSIRO, where they did lab trials and pot trials, and they showed the benefits for plants. And Sam Catalano at Innisfail produced and sold this crushed basalt called Min Plus. And Dan Gangimi continues to do that. Do you want to put your hands up? So I'm talking about here. Those fellas are sitting there, so thanks for coming along. So that's been a thing that's been happening, just within a couple of hours of here, and farmers are implementing that idea because of that production. There are other companies producing similar products around Australia as well. So generally speaking, in most situations, applying crushed basalt is good for soil. In the 20th century, we also became aware of this rise in atmospheric carbon dioxide and global mean temperature, and the human contributions to that. Sorry, I'm just juggling with arrows here. I'm not quite sure how this is working, but anyway, that's all right. I'll keep going. That's okay. So in the early 2000s, a few people started talking about the idea that adding alkaline silicate rocks to soil wouldn't only improve them, but could capture carbon dioxide as well. And so perhaps we can accelerate weathering sufficiently to make a significant contribution to the intentional removal of carbon dioxide. So how would we do that? We'd take basalt, which is often near the surface of the earth because it flows over the surface of the earth, mine it, crush it, spread it on land, and then the basalt reacts with the carbon dioxide in the water to give you some secondary minerals, to give you your cations and your bicarbonate, which leaches through the soil into groundwater, into rivers, and into the sea, where it's durably stored, because the sea is a big alkaline buffer, and so it's safe once it's there. So this is the equation, which is the same equation I showed you for the natural one. I just happened to have replaced calcium with magnesium, but it's exactly the same thing, and we're just looking at accelerating that process. So if the amount and value of the carbon dioxide removed exceeds the amount of carbon dioxide emitted in that process and the cost of doing it, then it's worth doing it. So to summarise the enhanced rock weathering idea, it's got a number of attractions, so potential to improve the soils, potential for CDR, carbon dioxide removal. The rocks that you can use, for example, basalt, abundant and widespread. So on the right there you can see paper with basalt outcrops in eastern Australia, pretty coincident with agricultural areas. Rocks are waste product of mines and quarries produced when people are producing aggregate. It's sort of a waste product that they want to get rid of. The land, technology and infrastructure are all available. We've been spreading lime for years and it's the same technology. So they're all the attractions. There are also, of course, some potential detrimental effects. For example, contamination if you use the wrong type of rock, or compaction or increase in mining activity and transport, etc., if we really scale it up. So we know that the hotter and wetter the climate, the more weathering you'll get. We know that the more biological activity, you've got more carbon dioxide, so that pushes the equilibrium, helps you remove it, so topsoils are good for that. We know that rock type is important. The higher the calcium magnesium content, the finer the particles, the more easily weatherable the minerals, the better it is. And what we didn't know 5 years ago, and we're just starting to get results of these sorts of questions, are what is the actual CDR? How much actually gets captured? And apart from that theoretical reaction, and what are the benefits and costs in the field, and how do they vary across different soils and cropping systems, etc. So let's go back to this graph. So when we add silicon rock, we could start with a soil which is anywhere along this sort of continuum. Starting with a highly weathered soil actually makes sense, because the more highly weathered soil, the more likely the added minerals are to weather. If you've already got weatherable minerals in there, you slow the weathering rate of the new ones. So highly weathered soils are good. They also tend to exist where you've got hot, wet conditions, which is also good. In Australia, not necessarily. We've got weathered soils over the whole continent. But anyway, so for the purpose of looking at this, let's start with a highly weathered soil, and we add some alkaline silicate rock. So the soil primary minerals aren't going to change much over this time period. We've gone down to a roughly 10-year time period, mostly because we've got mostly quartz, which doesn't weather. The added primary minerals, they're going to weather and disappear. Well, that's the aim. The variable charge materials, the organic matter and oxides, probably won't change much over that time frame. They might change a little bit. The organic carbon, that may go up or down, and this is a real interesting question which we'll be talking about today. So there's uncertainty around that. The pH will go up. We've added an alkaline material. It's weathering, so the pH is going to go up. The base saturation will go up because we're releasing calcium, magnesium or whatever, and displacing aluminium. And if we look at the carbon dioxide lastly, the initially model, or what we're hoping is that the carbon dioxide will be converted to bicarbonate, and the initially modelled sort of figures that were in the literature were reported at around about, there were many figures, but this was one that was reported and widely referenced, 2.6 tonnes of carbon dioxide per hectare per year modelled as being achievable. So do you remember the figure I said about the natural one? 2.8. So we're talking here around the same order. So here we've got a catchment which is fully basaltic, great conditions, and the modelling here was saying we can achieve that by adding tens of tonnes per hectare. So how does that amount compare to the global need for CDR that Annette was talking about? So this is a version of the graph that Annette put up. But it's got some numbers on here, and we're roughly here in terms of greenhouse gas emissions, or gigatons of CO2 equivalents here. So CO2 due to fossil fuels and deforestation's here, and then when you add the non-CO2 greenhouse gases, push it up to there. So we've got this commitment to get to net zero by 2050, and we know that we can't, we pretty much know that we can't get rid of all of those emissions, so we need the negative emissions or the carbon dioxide removal to reach that net zero. So here you can see that the net net carbon dioxide removals that were projected to be needed around about 10 gigatons per hectare, gigatons globally, David Beerling and his group in 2020 published a paper where they looked at deployment globally, and they estimated that employing enhanced rock weathering globally, or in a number of countries where it sort of would be feasible, you could capture in the order of 2 gigatons carbon dioxide per year. And when you compare that to the 10, that's huge. That's 20% of the requirement just in enhanced rock weathering. So that huge potential really made people sit up and listen to enhanced rock weathering. So a lot of activity has happened since 2020. We've now got probably more than 20 companies that are managing enhanced rock weathering projects globally. There's hundreds of millions of dollars invested. You can see here that the company mentioned here, Carbonaut in Australia. Where's Reese? Can you put up your hand? We've got Reese here from Carbonaut if you want to talk to him. And some of the other speakers here have got links with some of these other companies as well. So this commercial interest comes from the fact that enhanced rock weathering, it might provide extra income for the farmers, the mine and quarry operators, and all the project managers, brokers, auditors, lawyers, and so on. So a whole new industry that will be creating value. I think it's topical to go back to this graph and to mention one of the companies in a carbon credit issuance that was made last December. Lithos, a company based in America, were issued a credit of 8.3 tonnes of carbon dioxide per hectare per year by Puro. Now, I think that's implausible. And why do I say that? Because nobody's measured that rate anywhere in a scientifically valid trial. So the sorts of rates we're getting in field trials that are well-designed field trials now coming out is much lower than that. So we've got this big discrepancy between rates. Is it here or is it here or is it somewhere in between? What is the difference? Why is that so? And we're starting to work out, why is this low? So there's a whole lot of these soil properties that are causing it to be low, and you'll hear more about that. There's things like strong acid weathering, which is acids other than carbonic acid which do the weathering. And if that happens, you don't get carbon capture. So there's a whole lot of things that we need to find out. And you can see that, that divergence means research is critical. So the need for research has gained the attention of government and the research community. So we've got the carbon dioxide removal roadmap from CSIRO, which mentioned enhanced rock weathering as one of 4 CDR, feasible CDR technologies. And the carbon capture technologies program of the Australian government announced this year mentioned enhanced rock weathering as an eligible technology. So there's a lot of research already going on, so this is an excellent time to get together and to discuss our activities, our early results, our challenges, and we've got people here who are going to tell us about a whole range of interesting work on deployment modelling, societal acceptance, life cycle assessment, mechanisms of CDR, field trials in all these areas, pot trials, feedstock characterisation, and modelling of the processes. And at the end of the day, we'll have an opportunity to reflect on all of that and have an open discussion as well. So lastly, I'd just like to mention the project that's supporting this symposium. So the project has 2 aims. One is to determine the effect of crushed basalt application on crop production, soil health and carbon dioxide capture in diverse and important agricultural systems of Australia. And we're achieving that through 7 on-farm field trials in Eastern Australia. There's a poster on that outside if you want to have a look. To see what we've just started. The trials started in 2025, 2026. And the other aim is to increase adoption of the practice in situations where it has net benefits. And we're doing that through communication engagement with the agricultural market and regulatory sectors and the science sector, of course. And this symposium is helping us address that second aim. So thank you for participating and doing that. So in conclusion, enhanced rock weathering, it's promising for improving soils and crop productivity and for capturing carbon dioxide. We're in the midst of an exciting research boom on enhanced rock weathering, so let's get on with it and discuss it.